Yes. Okay, great. So I think we are underway. So yeah, we are very glad to have Professor Alexander Yong today from UIUC. He will talk to us about Newell-Littlewood numbers. Over to you.
Thanks so much. And when Apurva wrote me to give this virtual talk, I was really thrilled. It's like an early Christmas present. And I just want to let you know that I wanted the full virtual experience. So last night I went on YouTube and took a flight to Kempegowda Airport, first class on Lufthansa, by the way, and even took a tour of the institute. Went down the tree-lined streets and took a look at the building.
A very pretty campus. Hopefully, you can be here someday. Yeah.
Right. My morning coffee, I pretended to be from the Hatikap.
Oh, okay. You really did the whole thing. Great.
But it's sort of a metaphor because when I was viewing my talk, it reminded me that there were, so many different mathematicians with different origins that are represented. I mean, French, German, Australian, Chinese, American, Russian, and Indian. So I hope that you'll appreciate this talk from that perspective, that we're sort of taking a virtual tour, not only in space, but time. This is some joint work I've been doing with Shiliang Gao, Gidon Orelowitz, and Nicolas Ressayre. In my abstract states that we have 3 papers, but I'm mostly talking about the third, where we're all represented. And okay, so I will just start with the general linear group reminder. The general linear group is the group of invertible n by n matrices for me over the complex numbers. And the talk is about representation theory. So this is, or combinatorial representation theory. But we're discussing linear representations of a group, and this is just a homomorphism from your group to invertible linear transformations for some finite dimensional vector space. Now, discussions of representation of the general linear group could take, a good part of a semester course. So let me just give you a crash course in one example. Well, reminder that when you have a representation describes a homomorphism, you can also equivalently describe it in terms of modules. That is, you take your vector space V from the previous definition and just have your group element act through the homomorphism. And this is a module in the sense that really you extend this to an action on the group ring. Okay, so here's the smallest interesting example of this kind of general linear group representation theory. And I want to tell it to you because it comes up a little bit, at least in principle. So here, n equals 2. I'm looking at 2 by 2 invertible matrices, and I want to know how it acts on some choice of vector space. My vector space is going to be homogeneous polynomials of degree 2 in 2 variables. And okay, so this is the span of x squared, xy, and y squared. How I'm going to have the group act is by change of coordinates. So x maps to ax plus cy, y maps to bx plus dy. And since my matrix is assumed to be invertible, this is actually a change of basis. So you're mapping this basis to some other basis by using FOIL. And if you write down the change of basis matrix, that's this thing over here. This is the homomorphism from the first definition. So you have in this example both the description as a module and the equivalent description as a homomorphism. And this is a key example. One thing I'll just point out is that all the entries in this matrix are polynomial. And when you have that, then you say that this is a polynomial representation. I could also have rational functions, and that would be rational representations. But I'm just going to stick with polynomial representations for simplicity. And in fact, people know that that you can recover the other theory readily from the first. Okay, so polynomial representations. Reminder: the basics of a representation. The atoms are the irreducibles, and your irreducible representation if the vector space V only has trivial submodules. Okay, so traveling back in time to 1901, we have Isaac PhD thesis. His PhD thesis was that the irreducible polynomial representations of the general linear group are labeled by partitions. Partitions with at most n rows. So I'm not talking n boxes, n rows. And just the control picture is that if n equals 3, my integer partition, the decreasing sequence of non-negative integers, 4, 2, 1, can be described in terms of a Yong diagram. And at least where I come from, we draw it like this. 4 boxes in the first row, 2 in the second, and 1 third. There's also, by the way, French notation, Australian notation, and Russian notation, where you put it diagonally. So that's a function.
What's Australian?
Pardon?
What's Australian notation?
I think it's where you turn it like this. Right? Because it's down under.
Okay, very good.
Okay. Yeah, for the students who may not have seen this before, you know, in order to send representations, often you want to discuss some sort of notion of character. And in this case, the character is defined to be what happens when you take the homomorphism on a generic diagonal matrix and then apply the trace. Okay. If you're a student and you've been first exposed to finite group representations, I think it's a reasonable question to ask why it is that you can restrict to just diagonal matrices and not, let's say, all n squared variables, which would be, just an arbitrary element of the group. And that's because, because phi is a homomorphism and trace is invariant under conjugation, you can always, the character will be constant conjugacy classes. That's statement number 1. And then statement number 2 is that almost every invertible matrix is actually diagonalizable. And so therefore, by continuity, you can restrict to this case. Okay, so in any case, you therefore get a polynomial in n variables. It's a polynomial because we're assuming we have polynomial representations. In our particular example, I'm replacing A, B, C, D with just this generic diagonal matrix. And when you hit it through the homomorphism, you end up with this matrix, and the trace is this polynomial. You'll notice that the polynomial is symmetric, and that's for an obvious reason, because the definition of the character doesn't depend on how you name the diagonal entries. But actually, there's more that's true. It's not just any symmetric polynomial. These are actually a very beautiful basis of all symmetric polynomials. These are called the Sure Polynomials in honor of Isaac Scher's PhD thesis, I presume. And we're just going to take as a definition of the Sure polynomial as the character of one of Scher's irreducible representations. In our particular example, for those of you who know the notation, the representation we're dealing with corresponds to the Sure polynomial 2, 0. Okay. Now, of course, some of you may know, or many of you may know, that Sure polynomials can also be described in terms of semi-standard Yong tableau, and there's a whole subject of combinatorics that I make my living on somehow regarding that topic. Okay, the other basic concept that comes up in this talk is the notion of tensor product, which I know you know, but let me just state it because there's one slightly subtle point I want to emphasize for the students. Okay, so what is a tensor product? I have 2 vector spaces, and I'm trying to understand all bilinear maps from the Cartesian product. And what the tensor product says is that I want to posit the existence of some other vector space with the property that if I have a bilinear map from my Cartesian product to my tensor product and a bilinear map to some other vector space, there exists a canonical linear map from the tensor product to my other vector space. So this is the universal description of tensor product. And from the universal description, it implies that the tensor product is up to canonical isomorphism unique, which therefore only leads to the question of existence. And as you all know, the existence is obtained by writing down elements V tensor W and throwing down infinitely many relations so that you force the map from the Cartesian product to be bilinear. In other words, this is a fairly useless definition in practice, although it's great for proving existence. Okay, so in our situation, I'm going to assume vector spaces are GLN modules, and I'm going, so they're in the category of modules over the group algebra, but I'm going to take the tensor product over the field, right? And when you do that, you have an action of the general linear group in our case by the sort of diagonal action, okay? And so therefore the tensor product also inherits the property of being a GLN module. Next statement is that the general linear group is reductive, which just means in our instance that, that the representations can decompose into irreducibles. And so I'm going to do that. I'm going to take the tensor product of the irreducible, of the Sure modules, and decompose them into themselves. And you're going to see some multiplicity. Some constituents will occur with some multiplicity, the C lambda mu nu. Okay, and the basic question that kind of pervades this particular combinatorial representation theory is, how do you calculate these numbers? What can you say about these tensor product multiplicities? Now, there's a fortunate thing, to make use of the characters. We know the character of the irreducible is given by the Sure polynomial, and the Sure polynomials form a basis of symmetric polynomials, so we can multiply them together and, of course, therefore expand in the basis of Sure polynomials. And it's not too hard to show from the definitions that, in fact, this product and expansion exactly matches this tensor product, right? So the coefficient here is, in fact, the coefficient over here. I guess in fancier terms, you can say that this line is the categorification of that line. Now, another thing I should say to those who are not born representation theorists is that it's a reasonable question to just ask, okay, fine, we have these irreducibles, we have a notion of tensor product, they come from the textbook, so let's just tensor them together and expand and ask how many times something appears. But it's worthwhile to mention that really, like, if you were sort of coming back to basics and trying to go back to Sure's world and just try to construct the representations starting from things like this, you would naturally actually start coming to trying to construct more representations. You would actually do this sort of tensor product operation and decompose. So therefore, this question is not just a natural question in terms of words, but it really encapsulates, how you would try to do this sort of representation theory. And so in that sense, it's truly a basic question. Okay, I mentioned semi-standard Young tableau, and I want to tell you a little bit of combinatorics of how you compute these tensor product multiplicities. So in my business, they're called Littlewood-Richardson coefficients because of the work of Littlewood and Richardson. If you haven't seen this rule before, maybe it's easiest to explain it in terms of an example. Okay, imagine I'm trying to take the tensor product of v lambda with v mu and figure out how many times v nu appears. So lambda here is going to be this Young diagram, mu is that Young diagram, and I want to see how many times this big guy appears. And the way the theorem that I'm listing here works is that I take this biggest shape and I take away, the parking spots from lambda in the northwest. Okay, so I cut that out. And if lambda doesn't fit inside nu, then the coefficient will be 0 by fiat. So we're going to assume that that's possible. And you'll notice in my example, I smartly set it up so the number of parkable spots where the 1, 2, and 1 are exactly the size of mu, the number of boxes of mu. And again, if that wasn't true, then by definition, the coefficient is 0. Okay, so in this case, what you have is the mu has two boxes in the first row and 1 box in the second row. And so I'm going to put down 2 1s and 1 2. And there are 3 ways to do that right here, okay? And what we're going to do is we're going to read in traditional Chinese. We're going to read down columns from right to left, okay? True cultural talk that we're having, okay? And if I see, as I read in traditional Chinese, if I always see more ones than twos, then I'm good, otherwise I'm bad. So I see a 1 and then I see a 2, so we're tied, and then we see an additional 1, so we're good. So this is a good guy. Same thing here, we're very good. 2 1s before we see a 2. And this is a bad guy, because in traditional Chinese you see a 2 and then before you see any 1s. And that's what what we're calling the ballot condition. It's supposed to represent voting in some sense. So the general rule is that if you put down numbers like this according to mu, and you always see more 1s than 2s and 2s and 3s, 3s and 4s, then you're good, otherwise you're bad. And the remaining condition, the Littlewood-Richardson rule, is that you're semi-standard. And I intentionally made this condition vacuous in this example, but it just means that you're increasing weakly along rows and strictly decreasing along columns, okay? Therefore, in this particular instance, the tensor product multiplicity is 2, because there's exactly these 2 tableaux. Okay. If you didn't catch all that, that's okay. If you haven't seen this before, there's the main point I want to get across is not to remember this rule for the sake of this talk, is that you know that it exists and that you could understand it with 10 minutes of quiet. Because later on in the talk, I will say, by the Littlewood-Richardson rule, it follows that. And I want you to just know that, logically speaking, you could figure it out from this. Now we turn to the main sort of prototypical question of this talk. I want to characterize when the tensor product multiplicity is non-zero. I don't want to know what the number is. I just want to know when it's non-zero, which is even in some sense an easier question. Now, on the one hand, this question is idiotic, because your answer could just be whenever this crazy rule doesn't produce a tableau, right? And that would be an answer. The complaint would be that this algorithm of Littlewood-Richardson is fairly complicated, and the search space is exponentially large. So it's actually hard to actually, I mean, you can write a computer program to run this thing, but for relatively, not too large tableau, it becomes hard to actually, detect the entire space of them and reveal whether or not it's non-zero. However, I don't even care about that. I don't care about the computational complexity. That's not the interest here. My goal is to hopefully explain, if I say things correctly, that this question is actually interesting and has interesting answers. That's the purpose of the next several slides. Okay, I want to understand the structure of when these numbers are non-zero. And the first thing that you can deduce from the LR rule, the Littlewood-Richardson rule, is that these numbers form a semigroup. What I mean is that imagine lambda mu nu, this is a triple of partitions. Let me just call that a triple to save my breath. Suppose I have a triple where you have a non-zero coefficient, so that'll be a triple. And I have another triple, then when you add the triples together, that will also be a triple. And so that's semigroup structure, right? Therefore, that allows me to define LR semigroup. It's just going to be all triples of partitions where the coefficient is non-zero. And I want to study that, at least as a structure of a semigroup. Does that make sense? Are there any questions so far? This is the, okay. Okay, I hope it's understandable thus far. We have these tensor product multiplicities and we have this semigroup, and it's worthwhile to think about it. Now, the next thing is sort of strange. It's the same thing as the semigroup, except there's an extra, quantifier, okay? So in the subject, it's interesting to study the saturated LR semigroup. So what's the saturated LR semigroup? I'm going to take triples of partitions which may not give you a non-zero coefficient, but some rational multiple of your partitions will. So when you rescale the partitions with a rational scalar. And since I'm dealing with rational scalars, I might as well assume my partitions are rational partitions, meaning decreasing sequences of rational numbers. Okay, so we have the LR semigroup and the saturated LR semigroup. Evidently, this is contained in here because in this definition, I can always take t equal to 1. A theorem of Knudsen and Tau from last millennium, I guess, is that the LR coefficients are saturated. That means that these things, which are lattice points, are exactly the lattice points of the rational polyhedral cone that's generated by these points. Rational polyhedral cone means that you have some matrix P with rational coefficients, and that these vectors are exactly the solutions to this inequality. And so these things are in fact the same, they generate the same rational polyhedral cone, and therefore you could in principle forget the second definition, which raises the question why I even brought it up, because I could just, if they're the same. The point is that actually, while it's true in this situation they're equal, in general, they're not necessarily equal. And it's actually the second one that typically is the correct thing to think about, not the first. It's an accident in some sense that the first is equal to the second in the theory. All right, so I promised you that this question of non-zeroness has an interesting answer, and here's hopefully the proof of my claim. So a reminder that a matrix, an n by n matrix is Hermitian if it's equal to its conjugate transpose. And I'm sure all of your undergraduate students know the spectral theorem that Hermitian matrices are all diagonalizable and they'll have real eigenvalues. And so there is what your undergraduates may not know, unless they're taught by one of us, right, is that there's an old problem from the 19th century called the eigenvalue problem, which says the following. Suppose I have 3 Hermitian matrices. Okay, so we know their eigenvalues are real, and I can sort them to be decreasing order. So I can think of them as being, a bunch of partitions, real partitions, if you like. Okay, lambda, mu, nu, and there's going to be, a total of 3n entries. But now let me add the hypothesis that A plus B equals C. The question is, when you add that hypothesis, what constraint does that put on lambda, mu, and nu? What can you say about that? Is the question clear? Right? You have these lists of eigenvalues, you have an additional addition constraint, and you want to just ask, like, if I give you a triple of partitions, can you tell me whether or not it can occur? Okay, well, before answering that question, let me just define an answer. The definition of the answer is that it's going to be the eigencone. Eigencone is just going to be all triples of real partitions, which can occur as some matrices, for some matrices A, B, and C. And the name eigencone is justified by the following theorem of Klyachko. So Klyachko, a Russian mathematician working in Turkey, I guess, he was the first person to solve this eigenvalue problem. His solution, one of his theorems says the following. The eigencone and the LR sat cone are the same thing. They generate the same rational polyhedral cone px greater than or equal to 0. LR sat, remember, is this funny thing over here, and eigencone refers to this problem. And I mean, I think that answer is absolutely amazing. It's amazing that's true, because you could try to imagine a relationship of, what does representation theory of the general linear group have to do with eigenvalues of Hermitian matrices? Remarkable. And when you look at the, the papers, the survey papers, I think sometimes, it's hard to see sort of how stunning this result is. And I'd like to, I worked out a little example to kind of illustrate what's going on in Klyachko's theorem. and why I find his results remarkable, just at a guttural level, not because someone told me, just because you'll see it. Okay, so here's a triple. Here's an LR triple, meaning that if you apply the Littlewood-Richardson rule, V lambda times V mu contains this guy here. So this is inside LR sat because it's in fact even inside LR. What Klyachko is saying is that because this is an LR triple, he can find Hermitian matrices A, B, and C, 2 by 2 Hermitian matrices with eigenvalues 4, 1, 3, 1, because of this, and 6, 3, with the property that A plus B equals C. Okay? That's what he's saying. And so I'm going to actually do it. I can always conjugate by a unitary matrix to make any of them diagonal. So I'll just choose to make C diagonal. Okay, so I have control over that. But still I have to solve for A and B. So here's a general form of a Hermitian matrix, 2 by 2 Hermitian matrix. This is the conjugate, complex conjugate. And then this matrix is determined because of this linear relation. So there it is, okay? I need to solve for little a, little b, and little c. And I'm going to use Newton's identities. We know that the trace of the matrix is the sum of the eigenvalues, which I'm given. And the determinant of the matrices is the product of the eigenvalues, which I'm also, of course, given. And so I apply that to these two matrices, and you end up with, after a little bit of scratch work, you end up with two linear equations of A and C. And it turns out that the value, only the amplitude of B matters. And so therefore, when you solve it up, you end up with a complete parametric solution depending on this argument theta. So that's the complete solution. All of the possible solutions are obtained by conjugating everything by a unitary matrix. Okay, fine. So I could do that. But what's interesting is that when you vary lambda mu nu, sometimes you can't solve this because it depends on whether or not it is an LR triple. And when I mean maybe you can do it better than I when if you get bored during this talk, but it's hard for me to see without knowing the answer that you actually will have a rational polyhedral cone of solutions, even for the n equals 2 case, much less the general answer, which I'm about to show you. Okay, so this is, I hope, explaining what his theorem is about.
Alexander, from a historical point of view, weren't the inequalities known before the Littlewood-Richardson rule, or
some of the inequalities were
inequalities,
right? I mean, yeah, I will in fact discuss Horn's. Well, Horn is after Richardson, but they wouldn't even know each other. They wouldn't, as I shall explain. But there are inequalities that do go back to Weil and on all kinds of things. So yeah, it has a very long history of partial answers. I hope to explain history shortly in the next slide, actually. Okay, so what is the general answer that Klyachko gives? The general form of his inequalities looks like this. You're going to take partial sums of eigenvalues and have that inequality. And it's a little crazy seeming what the description is, but bear with me. The sum is over subsets of n. N is the size of your matrix. And the subsets are all of the same size T. Okay. His answer says that this is an inequality if a Littlewood-Richardson coefficient is non-zero. And tau here is, I'm sorry, this is the sort of thing that I'm sure that you could do when you prepare for your G, right? I mean, it's just the correspondence between subsets and lattice paths and partitions. So binomial coefficients, permutations, combinations. So if you have a sequence, a subset, you can arrange them in decreasing order and then subtract t minus 1, blah, 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 and you'll get a partition. So, you know what I mean, like when you have lattice paths, that's a partition, right? You prepare for that in the G. I mean, I know you do some combinatorics there, but maybe not that. Okay. Anyway, so now you have triple partitions and you ask whether this coefficient is non-zero. If you are, then you are a Klyachko inequality. If you're not, then you're not a Klyachko inequality. And so that's the thing that's hard to see from the previous slide. Like how, when you do this, you don't, it's hard to imagine that the answer is Littlewood-Richardson. Okay, so Klyachko's theorem is that, okay, first of all, the eigencone is the same as the LR sat, and not only that, he's going to describe exactly what the inequalities are, and it's these guys. Okay, so to your question, when you combine this result with Knudsen and Tau's theorem, you get something called Horn's inequalities. And I think it's a little bit tricky, I think anyways, to suss out exactly the relationship between various theorems if you're not exactly studying this stuff. So let me hopefully explain. Horn in the 50s had a list of inequalities that look exactly like this, except that his answer was not that the Littlewood closure is non-zero, it's that the smaller eigenvalue problem has a solution. So his statement looks precisely like this, except that it's only exactly within Hermitian matrices, no mention of Littlewood coefficients. What Klyachko was proving is that LR sat is the same as eigencone. What Knudsen and Tau prove is that LR sat is the same as LR. So therefore, by a trivial induction, you can replace this with a smaller Hermitian matrix problem. And so that's why Knudsen and Tau, when you combine with Klyachko, proves this older list of inequalities due to Horn. And that's what the history is. Is that clear?
So Klyachko actually refers to the Littlewood-Richardson rule.
Yeah, so I don't know exactly what he was thinking, of course, but his inequalities are precisely Horn inequalities where you make the change, where you replace this with, does there exist, a T by T Hermitian matrix A plus B equals C, right? That's, that was his conjecture. Now, Klyachko is saying that LR sat is the same eigencone, but this statement is not about LR sat, this is about LR. So since LR sat is equal to LR, therefore by induction on using Klyachko's theorem, Horn is true.
Okay.
That's the history. And I think it's actually a little bit difficult to get out of just the source literature just by quick reading. Okay, so I want to now turn to our results. The thing to remember as a summary is that we're going to give Newell-Littlewood generalizations of all of Klyachko's theorems for the classical groups. That's, long story short, that's what we're doing. Okay, so just a reminder of, so class groups are the special orthogonal groups and symplectic group. Reminder that the special orthogonal group means the following, right? You have some non-degenerate symmetric bilinear form, and then you just have some matrices which preserve the form. And by definition, orthogonal matrices all have determinant 1 or -1, and so the special orthogonal matrices are just those that have determinant 1. And then the symplectic group is defined the same way, except they use skew symmetric bilinear form, except in that case, the determinant is always 1. So that's why there's no such thing as special symplectic group. Weil, in 1939, in his book, The Classical Groups, extends essentially the example from the first slide of this talk. And what he does is that for every classical group, he constructs a representation for a partition of length at most n. These are all irreducible except in one special instance, which won't actually matter at all for this talk. Just for completeness, in the even case of special orthogonal group, and when the last part is non-zero. In that case, it's the sum of two irreducibles. Okay, so therefore, we can ask the question of tensor product multiplicity just like we did with GLN. We can take two of these Weil modules, tensor them together, and decompose into the irreducibles. Let's say if we avoid that case. And there's some numbers T lambda mu nu, T for tensor, that we would like to study. And of course, we can ask questions like, how do you compute them? When are they non-zero? And these, there are a lot of answers to this question that I hope to explain in the context of what we're doing. For example, for those experts, you'll know that there's Littleman path model crystals that allow you to compute this in great generality. However, I want to go back to something a little bit simpler than path model. I'm going to define, let's define the Newell-Littlewood number. This is not due to us, due to Newell and Littlewood. Combinatorially as a sum of product of Littlewood-Richardson coefficients, given by that definition. This is combinatorially defined because you remember I gave you a rule for computing the LR coefficients. So in principle, if I give you 3 partitions, you can compute any NL number that you like. This is N, that's T, they're not the same thing. However, Klyachko and Terada in 1987 proved the following result. Under hypothesis, these numbers are in fact equal. The hypothesis is that the length of lambda plus the length of mu is at most n, where n is your SO2n or SP2n, that n. Second statement, which follows from the first. In particular, this number is independent of which classical group you're working with. They're the same number for BC, types B, C, and D, if you know what I mean. Dynkin types B, C, and D.
Sorry, so when you say classical groups, you're specifically excluding type A for this slide.
Yeah, sure. The outside of type A. Okay. For these classical groups, yes, exactly. They're all the same numbers in that range. And a third thing that which doesn't really come up in this talk, but you may find interesting, is that, well, you recall that the Sure polynomials, they are the characters of the GLN representations, and so you get, all the combinatorics coming from that. There's a complete analog that Klyachko and Terada introduced. They have a basis of symmetric functions. I'll call it the Klyachko-Terada basis, which are the characters for this situation. That means that the structure constants are exactly the Newell-Littlewood numbers. So from that perspective, there's a very close analog to GLN theory. I would argue even closer than path model and so on, even if that's more general. Okay, so I've just restated the definition, and what happened is Orelowitz, Gao, Orelowitz, and I, we started our study of this by just basically trying to understand what you could know about these numbers from the combinatorics, just from this definition. And so we have a bunch of results, most of which I won't state here, but I just want to give you a sense of how you think about this from our perspective. So the first things that you would learn just by thinking about the definition the first 5 minutes or hour or so is that in fact the Newell-Littlewood numbers generalize the Littlewood-Richardson coefficients. They generalize it in the case that the number of boxes of nu is equal to the number of boxes of lambda plus the number of boxes of mu. Okay, so everything we're going to say is not only an analog, but in fact a generalization. Second statement is, let's talk about semigroup. Is it true that a triple of things here and triple things here adds up to be a triple? Yes, because you can reduce the case that these form a semigroup. So that's first 5 minutes kind of thing. There's one interesting thing that also is true from the definition, that this number is non-zero only if the sum of the number of boxes is even. So there's a parity condition. Okay, so those are sort of fun things you can learn from the definition. Okay, let's sort of mimic what goes on in the first half of the talk. I'm going to define an NL semigroup. It's just going to be all triples of partitions where the coefficient is non-zero, the number is non-zero. Fine. And I'm going to introduce the saturated NL semigroup, which is the exact same thing with that additional quantifier that we talked about. So it's complete analog. And we have a conjecture that would be the Knudsen-Tau theorem if it were proved. that it's not quite true that NL is the lattice points of this thing, but it is if you add the parity constraint. So this is the only thing that is a barrier to equality. Okay, I want to state a theorem with Gao, Orelowitz, and Ressayre. So this is the analog of Klyachko's connection to Hermitian matrices. Okay, so it's going to be a little bit more complicated, but the main point is that there is an analog. Statement is that I want to know when a triple is an NL sat, right? And the statement is that that's true if and only if there are three matrices of this crazy form, right? With the property that they sum to zero. And in that case, I'm going to take the eigenvalues to be lambda hat, mu hat, and mu hat, where I just take the partition lambda and then I reverse it and put negative signs. Because it's a 2n matrix, so we have to have 2n eigenvalues. This crazy set of, so this is conjugate, this is transpose. This crazy set of matrices is not actually so crazy. There's a reason for it. It's in fact the intersection of the symplectic Lie algebra with Hermitian matrices. And that is derived from a theorem about Kalyanico, and I'll explain why a little bit later. Okay, so we have an analog of the eigencone equals LR sat statement in this theorem. How about Klyachko's inequalities or Horn's inequalities? In our earlier paper with Gao and Orelowitz, we defined a list of inequalities that has some resemblance to the Klyachko inequalities. Well, it's going to be more complicated, but this is the main form of the inequalities. And again, it's the same thing. You're summing over subsets with some conditions. You have this condition of non-empty, empty intersection. You have some sort of size constraint. But the one I want to actually emphasize here is this last constraint. It looks horrible, and frankly, it is horrible, but it has a specific form. You'll notice that the definition of NL coefficient is you're summing over three LR coefficients where you go alpha to beta, beta to gamma, gamma back to alpha. In this non-zeroness constraint, you have alpha 1 to alpha 2, alpha 2 to beta 1, beta 1 to beta 2, blah, 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 on to alpha 1, back to alpha 1. So it's the same form as the NL coefficient formula, except with more of them. And therefore, this thing depends on sort of, in some sense, not NL coefficients being non-zero, but some sort of extended NL coefficients being non-zero. Okay. Our conjecture was that you are an NL sat if and only if you satisfy these inequalities. So this conjecture would be the analog of Klyachko's theorem. Okay, so now let me state our results. Theorem A with Gao, Orelowitz, and Ressayre is that in fact that conjecture is true. Okay, so this is the analog Klyachko's theorem is in fact true. And the main observation is what I'll call Theorem B. Let me explain Theorem B. If you have any of these groups, could be type E8, anything like that, you could define something called the saturated semigroup. So you're going to look at when the tensor product multiplicity is non-zero, not the NL coefficient, but the tensor product multiplicity. And that was studied before by people like Kalyanico and others. Now, in general, remember the tensor product multiplicity and the NL coefficient are not equal outside the stable range, outside that specific hypothesis range. Okay. But we can ask for the comparison. Let me take this thing here and intersect it with the par n and ask, is it equal to this? Well, if m is very, very large, then you are going to automatically satisfy the hypothesis. So therefore, this equality is trivial. That's in the range that m is greater than or equal to 2n. However, it's non-trivial in this range because those numbers may actually be different. What our theorem is saying is that they will, well, fine, they will in fact be different, but where they're non-zero is the same. So once you prove that, you can turn the question of NL sat into questions about the saturated semigroup, which Balkali and Kumar already studied. Balkali and Kumar, in an even more general context, studied this saturated semigroup, and they gave them minimal inequalities for this saturated tensor cone. And so therefore, our theorem B, together with the eigencone description, would imply the first minimal set of inequalities for NL sat. The Balkali doesn't imply our theorem immediately because you need to know this relation. And from those set of minimal inequalities, we can obtain those crazy set of inequalities that we had using some pretty heavy lifting in Tableau combinatorics, which I won't make you see. Just one other additional theorem that I want to mention is that we have an analog of theorems of King, Tolun, Tumazet, and Dirksen-Weyman. It's roughly of the form that if you're on the boundary of this cone, that means when all the inequalities are equalities, then the NL numbers in fact factor. And in our case, a factor is a Littlewood-Richardson coefficient with a quote unquote smaller NL coefficient. Well, it will be smaller, but in other senses as well. Now we don't have everything though, okay? So, but what corollary F here is saying is that there's more to do. What is it there's more to do? What we can now show is that if the NL saturation conjecture that we had stated 1 or 2 years ago was true, then in fact, it's not only true that NL sat is governed by the extended Horn inequalities, but even NL itself, the thing without the extra quantifier, is described by those inequalities. That would be the analog of the Knudsen-Tau theorem, and that we don't have. We do have some evidence for at least this implication, this statement here. And in our first paper on the subject, we checked it for n equals 2 with some pretty hard effort, actually. And we also proved it in some other additional cases. What theorem A lets us do in our last paper is that we can actually prove that this assertion that NL is governed by those inequalities is true for all n less equal to 5. Now understand, that's not saying the number of boxes is 5. There's an infinite list of possible partitions with at most 5 rows. And we can prove computationally that all of those statements are true. And so therefore, that's our strongest evidence of at least this implication. Thank you.
This was, yeah. Yeah, it was lovely talk. Thank you, Alex. For, yeah. Are there any questions, comments?
Yes, Apurva, I have a question. That was indeed a very beautiful talk. I hope to go back to it. I guess it's being recorded, is it?
Yes, it will be on the YouTube channel.
Yeah, okay, thank you. So I'm not sure if this is a reasonable question to ask, but the first question is, so there was a theorem of Horn as well, right, in the earlier case, in the classical case. So with this, you had this complicated matrix form, which was implied by Balkali-Kumar. Yes.
Yes, so, correct.
Is there a Horn theorem there?
That's a wonderful question. I confess I've, of course, thought a little bit about some of the other variations of this Hermitian matrix eigenvalue result, and I don't have any other such theorems. So yeah.
Okay.
I think your question is very valid, and yeah. Yes, I'd like to know answers like that, but I don't have them.
Okay, thank you. Thank you.
And so, okay, in fact, this is also a question I wanted to ask here. So very naively, I look at the right hand, the set to which M1, M2, and 3 belong. And you said that, so these are first of all complex matrices A and B, because you're taking these conjugates.
Yeah.
And then, A is adjoint. A is what do you call it? Self-adjoint, I guess that's what it's saying. B is symmetric.
Well, yeah.
Yeah. So if A is self-adjoint, then of course, oh, okay, and B is symmetric, then the whole thing that you describe here itself is Hermitian as well. I guess. Okay. Okay. And then.
So Hermitian and symplectic, I guess, in the Lyon.
Right. Oh, okay. Yeah, and symplectic as well. Right. That's the point of the special form. Okay. Oh, sorry.
Yeah. Yeah. The point of the Hermitian is that it's, well, okay, really it should be anti-Hermitian. Is that's the Lie algebra of unitary. That's matrices. That's what's really going on here.
And the symplectic kind of suggests the form of that lambda hat, I guess, something.
That's basically because the Klyachko theorem says that you can use any class group you feel like to study these problems. So we're going to use the symplectic one. That's the reason why symplectic is coming up. We could probably do something, obtain essentially the same result with SO, right?
It's a bit, how do you end up like knowing that they're all the same? Do you work with each of them separately and get the same answer, or is there some?
You meaning in 1987? You mean?
You're asking how Klyachko and Tirada?
Yeah. Or well, how do you think about it? Is there some way to get them all, or do you just work with each one separately?
Yeah. So I suspect they actually have two bases, which of course have the same structure coefficients, and they work out both of them. I'm guessing that that there's, yeah, I forget, or maybe never knew. I have to admit, yeah. Sorry.
Also, is there this definition of Newell-Littlewood numbers? It seems a bit, I mean, of course, like, to the unmotivated, it looks weird. I mean, is there some way that one can explain why this kind of thing would arise at all?
There are these things like Littlewood identities that come up in their paper, and I mean, I guess I can't really express it in very simple verbal terms, but I guess I would just ask you to look at Klyachko and Tirada. I don't have a great answer.
Right. It's very, very beautiful.
But one thing you could think about that did come up in our work is that you could replace, for example, product of 3 with product of 20, right? Actually, one thing, okay, this is very sensitive to the situation. For instance, there are a lot of structure coefficients in representation theory that you could think about, or Schubert calculus or whatever. Let's just say Kronecker product, right, for a symmetric group. You could say, well, maybe there's an NL, like what you're doing is you're taking structure coefficients, compiling it this way and getting more structure coefficients. So you wonder, when is that true? And I have to say that I thought that it should be true at least some other time. And I found no other interesting example where it's true. So for instance, if you replace this with Kronecker product, formally you could make a definition. It doesn't produce a structure coefficient. If you replace it with various Schubert calculus things, you could make a definition like this and you don't get structure coefficients.
You could even take any associative algebra and
yeah, it's rare. It's surprisingly rare.
Wow.
When you say it doesn't produce such structure coefficients, is there some axiom that structure coefficient should satisfy, or we don't know an object of which this is the substructure coefficients?
Okay. So it can. So let's just suppose you're working with a ring with lambda, mu, and nu as your basis, right? Like just like Sure Polynomials, and you take anything that's indexed by lambda, mu, and nu that you have as structure coefficients, like let's say Schubert calculus of orthogonal Grassmannians or something like that, right? And you throw down a definition like this, and you ask, is there a ring with the property that product of lambda times product of mu has this many nu's appearing? You could define a pseudo ring that way and ask, is it an associative commutative ring? And the answer is that, in my experience, never, except for this case.
So just axiomatically, not even, okay, thanks. Yeah.
Just literally like write down a multiplication table and ask if it defines an associative ring. So it's a miracle.
One of many in this talk, I think. The fact that you can do all these things also for the NL numbers is pretty remarkable.
Right. Well, our conjecturally, like NL size equal to NL. So that means that we are in the same sort of situation as type A, where in fact you have equality of those things. In general, it's known that the tensor sat is not the same as the tensor cone.
So for example, in which cases or for which settings, for instance?
For type, I think for type B, it's known in general that's not true. It's conjectured to be true for type D. So therefore, NL is even in that sense more spiritually connected to LR than the very general context.
Right. You found the right way, the right place where the SAT equals the non-SAT. Right.
There are other cases, but this is somehow, you know, I mean, for example, you have symmetric functions, for example. I mean, that's you don't have. I mean, you of course have characters, right? You have vowel character form, but you don't have symmetric functions in type E8 or something, as far as I know.
Yeah, one of our other colleagues is missing here. He would be very happy to look at symmetric functions. Arvind, I don't see him here. Lyon. I think, but this FIPSAC is going on in Israel right now, so he's busy with FIPSAC because he's one of the invited speakers there as well. So anyway, but okay, yeah, further questions, comments?
So do you have any results for the branching coefficients?
Do I have any evidence? Sorry.
Results for branching.
For the branching, so you can restrict the representation. The tensor product is a special case for the restriction problem, right? So do you have any results for this NL coefficients for the branching problem?
We don't have any. Right. So is there an NL branching number? And I don't know of it actually. Maybe, but I don't know. Yeah, that's right.
Okay, thank you.
Mm-hmm.
How morally similar are NL and LR? Yeah.
NL and LR. Yeah. Well, one thing where they're morally not similar is, like, you know, if you look at this definition, you can construct a combinatorial rule, right? I mean, just by taking any model for this and just sort of gluing them together. Okay. However, it's actually, the answer you get is complicated. Like, for instance, in LR, you have, canonists have puzzles, right? This is sort of a planar thing. So if you know what I mean. And so if you just use their puzzles and glue them together according to this definition, you're going to get some sort of non-orientable surface. It's kind of nasty, right? So therefore, we don't have like a simple combinatorial. I mean, I don't know what does simple mean, but we don't have like a really beautiful ballot rule for NL. You know, something you want to show your mother, that kind of thing.
And also, since we are talking about moral similarities or not, if you have the basis of symmetric functions, is there also something like skew symmetric functions in this context, which somehow the NL numbers relate to?
Yeah, so the funny thing about skew is here, notice the NL coefficient is actually symmetric in lambda, mu, and nu. And so somehow there's morally there's no such thing as skew. I think. However, you could ask for QT deformations, and I think there has been work done on that by Shimazono and Zabrocki.
The QT deformations of these symmetric functions, you mean?
I think that's right.
Right, right. Okay.
Using, these creation operators, this kind of business.
So again, they obtain some eigenfunctions of some operators and so on.
I think that's right.
Oh, wow.
I mean, yeah, there's a paper in Journal of Algebra by Shimazon and Zabrocki. So, yeah, I mean, maybe I'm mistaken in my interpretation, in which case, you can look at it and see.
Right. Oh, this is a whole new world. So I really didn't know about these things, and how much they can go ahead as well. Wow. Thank you. This is really nice. This is really, really nice. Further questions, further comments? Okay, if there are none, then finally, let's thank Alex for a wonderful talk. It's really wonderful.
Indeed, that was a great talk. Thank you.
Yeah.
Thanks so much. It's been a real pleasure to be able to make contact with you guys.
Yes, it's been several years, but